We are continuing our discussion of two means in Chapter 10 here, in the second part of Chapter 10. This is our third lesson in Section 10.2. All right, so we talked about the difference in means and comparing two different means, sort of in general, about what the sampling distribution is going to look like. We also looked at constructing and interpreting confidence intervals, and in this third part of the lesson, we are going to talk about significance testing for the difference in two means. So that's what this 10.2.3 lesson is about. All right, so an observed difference between two sample means can reflect an actual difference in the parameters, or we could be getting that difference just by chance variation when we are sampling. So we're going to take two samples from two different populations, and then we're going to look at how different they are and try to see, does that imply, or can we infer that the true parameters, the true means from the two different populations are truly different? Or do we have evidence that they are the same? The null hypothesis here is going to be that mu sub 1 minus mu sub 2, the means from the two different populations, that their means, that the difference in their means is going to be some hypothesized value. Now, more often than not, that hypothesized value that we're going to be interested in is 0. Now, a word of caution, we're going to show you how to use your calculator to do this test, the significance test for difference in two population means. If the hypothesized difference is not 0, you cannot use your two sample t-test in your calculator. You have to do it by hand. Your calculator is set up only to evaluate the evidence against the null hypothesis when the hypothesized value is 0. Now, when we did difference in proportions, we said we're going to limit ourselves to only looking at 0. Here, we could potentially look at something other than 0. Most of the time, the difference in the two population parameters the null hypothesis, the hypothesized difference will be 0. But it doesn't have to be. So if they're equal to 0, then we can do a little math and actually get that mu sub 1 is equal to mu sub 2. If this value is not equal to 0, then of course we can't say that mu sub 1 is equal to mu sub 2 because we think that their difference is bigger than 1. So we think that mu sub 1 is 1 bigger than mu sub 2, or whatever the case may be. There is a homework problem dealing with the amount of water used in two different brands of flushing toilets. And so we don't think in that problem, gosh, I can't remember the exact value, but we think that one toilet flushes a half a gallon more than the other. So that means the hypothesized difference, mu sub 1 minus mu sub 2, the difference in the mean amount of water used by one brand of toilet will be a half a gallon more than another, something like that. I don't remember what the exact value is, but it's not 0. So you would not be able to use the significance test in our calculators that we're going to show you how to use in that rare case when the hypothesized value is not 0. Okay, so the alternative. So the alternative is that they're not going to be equal. They're going to either be less than, greater than the difference, or just not equal to if we don't have an inclination as to what direction it is or which mean is bigger. So we're going to say that mu sub 1 minus mu sub 2 is not equal to 0. That will be a two-sided test. Mu sub 1 minus mu sub 2 is less than 0, or mu sub 1 minus mu sub 2 is greater than 0. So a word of caution here too. Make sure that you establish which way you're subtracting the mean populations, and then you cannot flip-flop that throughout the problem, or you're going to get some weird results. So make sure that when you set up your state, that you are establishing which one you're essentially thinking of as mu1 and which one is mu2, subtract them in the direction, and then maintain that consistently through the problem. Now, when we go the alternative here, then rather than writing them like this, your calculator will tend to write them like this, where mu sub 1 is not equal to mu sub 2, mu sub 1 is less than mu sub 2, or mu sub 1 is greater than mu sub 2. Okay. So you can see here that if we do this, and then the test for this is going to be a 2-sample t-test. Our calculators are abbreviated as 2-samp t-test. You can see where the alternative selection kind of agrees with this alternative way of writing the alternative hypothesis. All right, so the test, the test statistic that we're going to use, you can see it's starting to get pretty complicated. It's the difference in the sample means, x bar sub 1 minus x bar sub 2, minus the difference in the hypothesized value. Again, more often than not, that mu sub 1 minus mu sub 2, the hypothesized difference in the means is going to be 0. Doesn't always have to be, but often it's going to be 0. But in general, you can see this formula is getting more and more complicated, and so we're going to suggest that you run the significance tests using your Texas Instruments calculator. Okay, so remember too that when we do a significance test for difference in t's, we kind of need to know the degrees of freedom. And so we're either going to let our calculators run it and tell us what the degrees of freedom are, or if we have to do it by hand and we use a t-table, then we're going to use the smaller of n sub 1 minus 1 or n sub 2 minus 1. Now, often our n's, our sample sizes, will be the same, in which case you would just choose one of the n's, but they don't always have to be exactly the same. We would like those to be similar. All right, and so again, we have if the difference is greater than the hypothesized value, it's a one-sided test. The tail is on the right. If it's less than the hypothesized value, then the tail is on the left. And then if it's just not equal to, then remember it's as extreme or more extreme than the statistic we get, but in both directions. So the p-value will be twice as large when we're doing our two-sided test. And again, a calculator knows that if we set up our alternative hypothesis as a two-sided test, it will double the p-value for us. But if you're doing it by hand, you just know, you have to make sure that you remember that you're going to double that p-value. All right, let's look at an example. So after buying many helium balloons, only to see them deflate within a couple of days, Aaron and Jenna decide to test if helium-filled balloons deflate faster than air-filled balloons. To find out, they bought 60 balloons and randomly divided them into 2 piles of 30, filling the balloons in the first pile with helium and the balloons in the second pile with air. Then they measured the circumference of each balloon immediately after filling, the balloon with either helium or air. And then they measured the circumference again 3 days later. All right, so what they did is they looked at the average decrease in the circumference. So a big number here means that the balloon lost volume, lost its size. So the average decrease in circumference of the helium balloons was 26.5 centimeters. All right, so that's the average for our one treatment group. They also give us the standard deviation, 1.92. All right, so those are both statistics from the helium group. And then the average decrease of the air-filled balloons was 2.1 centimeters with a standard deviation of 2.79 centimeters. Again, those are the statistics for the air-filled treatment group. All right. The question we have to ask is, do the data provide convincing evidence that helium-filled balloons deflate faster than air-filled balloons. All right, so that tells us, right, that we're thinking our alternative hypothesis is going to be that the number should be bigger for helium, because remember the number is the average decrease in circumference per balloon. So we think the helium number should be bigger than the air-filled, if that's what this is what the question's asking, right? Do we have evidence that the helium loses air faster than the air-filled balloon? All right, so the state. So we want to perform the following tests. So the null hypothesis is that there is no difference in the deflation rate, how much they deflate over time. So that the mean, the true population mean deflation or decrease in circumference for helium-filled balloons minus the mean decrease in circumference for air-filled balloons is going to be equal to 0. Now, the alternative, which kind of more agrees with our calculator, would be that mu sub h is equal to mu sub a. The alternative, now again, you got to make sure that you're being careful with the question, right? The question is there evidence that the helium-filled balloons deflate faster or have a bigger decrease in average circumference? So we think that mu sub h should be greater than mu sub a, or that mu sub h minus mu sub a should be a number bigger than 0, should be positive, right? All right, so either one of those, the green one there kind of more agrees with what your calculator, the way your calculator works with this. All right, we also want to talk about the 5% level of significance, right, the alpha level. And then we want to say what mu sub h and what mu sub a are in context, right? So mu sub a is the true population mean decrease in circumference of helium-filled balloons. And mu sub a is the true or population mean decrease in circumference for air-filled balloons. All right, so now let's work on the plan. What is the inference procedure here? And check your conditions, pause the video, and write that out. All right, so the plan, we are going to conduct a 2-sample t-test for difference in mu. You can say just difference of mu or actually write out what that difference is. So this is kind of helpful for, the first way of writing the null hypothesis that mu sub h minus mu sub a is equal to 0. So it's the difference in the mu's. And then we randomly assign the balloons to treatment groups. We did not randomly choose balloons. We randomly assigned the balloons to 2 different treatment groups. Remember, this is an experiment. And then the 10% or independence, we don't really have to worry about this because we're not sampling without replacement. This is an experiment, so we don't have to worry about independence. Our 10% rule. And then the last thing, each of the treatment group sizes was 30. So the central limit theorem says that the sampling distribution of the difference in x bars should be approximately normal. So we're safe to proceed with our T procedures. All right, the do. So I'm going to show you how to do this by hand, but again, we're really also wanting you to start doing this with your calculator. So if you're doing it by hand, go ahead and write out your do, pause the video, write out what your T statistic is, think about your degrees of freedom, find your p-value. If you're doing it by hand, do that using your t-table. All right, so the t statistic, again, we're going to use our formula here. The hypothesized difference is 0. That gives us a t statistic of 39.46. Again, if we're not using the calculator, we're stuck with the degrees of freedom of 30 minus 1, or 29. Now, how do we find the p-value? Well, if we're using the t-table, we simply go to our row 29, and then we look across that row, and we look for our t statistic of 39.46. Well, there is no number even close to 39.46. The biggest number on the far right side of our table is 3.659. That corresponds to a p-value, a pretty small p-value of 0.0005. So our 39 is so much larger than the last value that we know the p-value has got to be even smaller, so it's significantly smaller than 0.0005. All right, so it's way much less than that. We know, as it turns out, we could also use our TCDF. Now, we maybe haven't used this very much, but TCDF is just like our normal CDF, right? Our normal CDF gave us the shaded region within an upper and lower bound on a normal distribution. Here we can look at the same kind of thing for a T distribution, so a TCDF. All right, so we have to think about, all right, well, what's our lower limit? What's our upper limit? We don't have to say mean and standard deviation because it's a T distribution, which is already a normalized one. So all we need is the degrees of freedom. So it might help if we kind of think about, well, what's our graph look like? What's our T distribution? So our T statistic of 39, remember our alternative hypothesis is that the difference is greater than 0. So that would mean that we're on the right tail, shaded region. Now I've not drawn this, I've not got this drawn to scale. I'm showing a little bit of shading. In reality, that T statistic, the 39.5, if you will, is so far down into that tail that we really, really, if this was drawn to scale, you would not see any shading. But I kind of brought it back a little bit so that we have a little bit of shading there. So the lower bound is going to be our 39.5, 39.46, if you will. The upper is 1,000 degrees of freedom of 29. And that gives us a really small value. That's, 4.67 times 10 to the negative 27. So that means we would move that decimal to the left 27 times. So it'd be 26 zeros in front of that 4. So really, really, really small. So we say approximately 0. Resist the temptation to just call that 0 because it's not truly 0. It's just really, really small probability. All right, so now let's go and look at how we might do this instead of doing it by hand. How are we going to do this in our calculators? We're going to really encourage you to do that so that it's a little bit less accident prone. All right, so the test is called a two-sample t-test in our calculator, standing for a two-sample t-test for the difference in mu's. All right, and in our case, we're going to choose stats because we have the statistics. We do not have the 60 pieces of data, the 30 for each treatment group. So we have to instead, if we did, we would put the 30 data values for each treatment group in 2 different lists. And then we would use data, but here we have the statistics. We have the X bar and S for each of the treatment groups. All right, so we put those into our calculators. And then our alternative is going to agree with our alternative hypothesis up above. And again, it kind of agrees better with the green version of our alternative, null and alternative hypotheses. Remember, too, that we never pool the data for differences in means. All right, and then we hit calculate, and we get this as our output. And so remember that when you do this in your calculators, it feels like cheating, but it really isn't. We really are more interested in your interpretation of the results rather than the calculations. Okay, so we want to record these 3 things. We want to record the degrees of freedom. Notice the degrees of freedom of 51.4 first. It's not always going to be an integer once we have these difference in means. Other than it's very different than the 29 that we estimated it by hand. So the calculator gives us 51.4 is the degrees of freedom. The T statistic is 39.46, just like we calculated it before. And then the P value, again, really, really small here. And And again, it's a little bit different than what we calculated before, but that's because our degrees of freedom were off when we ran it before. Okay, so you could say approximately. That's what the squiggly equal sign. Don't say equals 0 because the p-value is not equal to 0. It's very, very small. So a squiggly equal sign, approximately equal to 0. And then also remember your shaded t distribution with labeling. And again, I didn't draw that to scale. In reality, we wouldn't see that little bit of shading out on the right side. I drew it so that there was a little bit of shading out here. In reality, we would not see that if we drew that to scale. All right, and so now let's think about the conclusion, the last part that we want to write. We want to compare our p-value to our alpha. We want to reject or fail to reject, and then talk about the evidence for HA. All right, so our p-value of approximately 0 is less than our alpha of 0.05. So we're going to reject the null hypothesis. And since our p-value is so small, we are going to, it'd be appropriate to say that there is strong convincing evidence that the helium-filled balloons deflate faster or have a larger decreasing circumference on average, right? Their mean decreased circumference is greater than that for air-filled balloons. All right, and then part B is asking us to interpret the p-value. So how do we interpret p-value? Write that out, pause the video, write that out, and then start up the video again. All right, so assuming that the null hypothesis is true and that there really is no difference in the mean decreasing circumferences for the helium, since the decrease is the same for helium filled balloons and air filled balloons, then we would see that there would be about a 0, very small, approximately 0 probability of getting the results as different as what we found, which was 24.4 centimeters circumference difference in the two means just by chance alone. So it's pretty unlikely that this could have happened by chance. And so what's really happening is that the helium-filled balloons indeed deflate faster than the air-filled balloons. All right, so I'm going to show sort of what the components that you got to make sure you don't forget here. So the first 4 state you want to do your null and alternative hypothesis. Don't forget about your significance level, and then say what those the mu sub h and the mu sub a stand for. So four things that we'd be looking for in the state part. All right, and then in the plan, you want to, of course, state your hypothesis, your inference procedure that we're using, right? So the 2-sample t-test for the difference in mu's. Your conditions, you want to check that you used random, right? You want to check your independence, or 10%. You want to check for the central limit theorem for both samples, or in this case, both treatment groups. And then, again, we're gonna assume, we're going to encourage you to use your TI-84, so your 2-sample t-test. So say that you're using that, but then also when you're finished, we want 4 things. We want the degrees of freedom, we want your t statistic, you want your graph with labeling and shading, and you want your p-value. And then the last step, your conclusion, 3 components to that. You want to say that you are compare your p-value to your alpha, decide whether you're going to reject the null hypothesis, and then do you have convincing evidence of HA. All right, so make sure that you've got that. We're getting more and more complicated here. We have about 15 components that we want in this 4-step process. All right, so some things to be careful of when you're using your T procedures. If possible, if you're running this test, you want your sample sizes to be as similar as possible. They don't have to be exactly the same, but if you can, we make those the same. We never pool the data in when we're doing T procedures. We only do pool the data when we are working with significance tests for proportions, for two proportions. We don't do it for the significance test for two means. So basically, the calculator is smart enough to know when you're doing a significance test for two proportions that they're going to pool the data, and it doesn't even ask you if you want to. Here, when you're doing this in the calculator, it'll ask you, but so if it ever asks you whether you want to pool the data, you basically say no, because it doesn't ask us when we're doing two proportions. It only asks us for two means, and we never want to pool the data for those situations. So always say no when the calculator asks. All right. We talk often about doing two samples from two different independent populations, but you can also use these T procedures for two samples when you are doing a randomized experiment. So you're not really sampling, you've got two treatment groups, but it is okay to use the same procedures for randomized experiments with two treatment groups. Remember too that we don't use a two sample T procedures with paired data that we saw in the last couple of chapters. So paired data, that is when we have one sample from two different, one sample, and we do two different things to that sample, right? So one, you become your own matched pair, right, in an experiment. So 1 week you do one treatment, and then the next week you do a different treatment. So the two treatment groups are not independent of each other, because the same treatment group got two different treatments, one after the other. Of course, which one you do first is determined by random, but they're not independent groups. And so we cannot use two sample T procedures on paired data because they're not independent groups. It's really the same group or related groups. All right, and then also be careful if you don't have randomization, either by randomly sampling or randomly assigning treatments, then we cannot use these two sample T procedures. All right, so what the next couple of slides are looking at is giving us a situation and asking us a question that we want to answer, and then you have to decide which of the procedures we're using in this case. So it's either going to be two proportions or two means, and then sometimes we'll use paired data as well. So what we want to do here is read through the question, read through the situation, and then decide which of these 6 inference procedures is most appropriate. So let's read through it. So do women have more friends than men? 83 women and 78 men are asked how many friends they have. Okay, so the first thing you want to think about is, okay, is this proportions or is this means? So the data we're collecting, are we asking yes, no questions, or are we collecting data and then going to average them, all right? Also, we want to ask ourselves, are we testing a hypothesis, or are we answering like a yes, no question, right? So if we are answering a yes, no question, then that is testing a hypothesis, right? If we're trying to estimate a difference in values, then we would be using a confidence interval, right? So a confidence interval is trying to estimate how different something is. A hypothesis test is there a difference? Is the difference zero, or are they the same, or are they different? So if you're answering a yes/no question here, then we're talking about a hypothesis test. If we're trying to estimate what a difference is, then that's a confidence interval. So let's read through for this first slide. Let's read through the different inference procedures, and figure out what we're doing. So, is this a confidence interval, or is this a hypothesis test? So, let's think about first. Do women have more friends than men? So that's a yes/no question. Like, is the difference zero, right? So this sounds like a hypothesis test. We're not trying to estimate what the difference is. That would be a confidence interval. So we know we're talking about, these top, not talking about these top three, because that would be trying to estimate using a confidence interval. Instead, we are trying to determine, is the difference between the men and women the same, or is it zero? So we know we're talking about a hypothesis test on the bottom here. Is it a hypothesis test between two population means? So we're talking about means here, or are we talking about proportions, which would be the last one? And then paired data. And remember, paired data always deals with means and not proportions, right? So is this proportional, or is this mean? So if you think, we're asking how many friends they have, so each person is going to give us a data value, a number. And so we're talking about means in this case. So I think you could see that we're definitely talking about a hypothesis test for difference in population means, not proportions here. All right, let's look at the next one. All right, so how much more often do women order dessert compared to men? 85 men and 73 women at a restaurant were observed to see if they ordered dessert. So, are we answering a yes/no question? If we're answering a yes/no question, then we would be dealing with a hypothesis. If we are trying to estimate a value, then we're dealing with the confidence interval. So think about what your response is. So in this case, we're trying to estimate how much of a difference there is. So definitely looking at confidence interval. Is this a mean, or is this a population proportion? Remember, we're asking sort of like, do you order dessert or do you not order dessert, right? So we're looking here at proportions. So it's definitely a confidence interval in the difference between two population proportions, because we're not asking how many desserts you order, but either you order dessert or you don't order dessert. Definitely a proportion. And so we're trying to estimate the difference in the proportions for men and women. All right, next one here. Does holding on to a crystal that's like a rock, right? A crystal, improve psychic ability? All right, 5,000 people are asked a question to guess the outcome of a coin toss. First without the crystal, and then while holding the crystal. This one's a little tricky, so pause the video, read through it, and then make a guess at which one it is. All right, so this one is a difference in proportions, right? So you're looking at 1,000, you're asking whether people guessed correctly holding versus did they guess correctly not holding. So it's they asked a yes/no question, right? I mean, did you guess correctly? Did you not guess correctly? So there's only two options. So it's definitely proportions. And then we want to know, answering a yes/no question, does holding the crystal improve the proportions of times that people answer the question correctly or not. So at first it sounds like this would be a matched pair situation, but it's definitely proportions because you either have success or you don't have success, yes or no. So it's definitely proportions. And so you can't really treat this as matched pair because it's proportional data, not means data. All right, so that one was a little bit tricky. Let's go on to the next one. All right, how much does personal spending increase after a tax cut? So 1,500 people were studied before and after a tax cut. So again, think about whether this is a confidence interval that they're asking us to talk about or a hypothesis test. And then think about the data, right? How much does personal spending increase after a tax cut? So it does sound in this case that we're trying to estimate a value. So it sounds like a confidence interval. And then we're looking at 1,500 people were, what was their spending before and what was their spending after. So definitely a matched pair in this case because the same 1,500 people were used, and we're looking at mean data. So we can treat this as, we can't treat it as two separate samples. We have to think of this as the same 1,500 people. We observed them before and we observed them afterwards. So how much money did they spend? We're trying to estimate the difference in the amount of money spent. And so definitely paired data there. All right, next one. Are art museums better attended on rainy days rather than on sunny days? Attendance numbers at the City Museum of Art were examined for 100 rainy days and 300 sunny days. So think about, are we trying to do a confidence interval? Are we trying to estimate something? Or are we trying to say, is there a difference? So that would be a hypothesis test. So which one is it? All right, so we're definitely looking at means, right? We're not looking at, well, first of all, we're doing a hypothesis test. So are museums better attended on rainy days versus sunny days? So yes or no is the answer. We're not trying to say how much better is the attendance. That would be a confidence interval. And we're looking at, how many people show up on rainy days versus how many show up on average on sunny days. So that's definitely population means. And so a hypothesis test for difference in population means. All right, next one. What is the income difference between Republicans and Democrats? Income data for 400 Republicans and 600 Democrats were collected. So is this a confidence interval or a hypothesis test? And then think about whether the data is proportions or means. All right, so in this case, we're trying to estimate what the income difference is. And so it's not proportional data. This is mean data, right? We would look at the average income for Republicans versus average income of Democrats, and we're subtracting that difference. So two population means, but we're trying to estimate what that difference is, so we're using a confidence interval. All right, so 65 monkeys were part of an experiment where they were each placed in front of a computer for 3 hours to learn 10 words. They were then given a 3-hour lesson from a human to learn a different set of 10 words. The number of successful memorized words from the computer lesson and the number from the human lesson were recorded. How much more effective was the human lesson? All right, pause the video and figure out which inference procedure, and then unpause the video once you've decided. All right, this one is definitely paired data. So it's the mean number, right? It's the same 65 monkeys. Each monkey is acting as his own matched pair, right? Each monkey learned words. How many words did they learn from the computer? how many words did they learn from the human? And so we're looking at the difference in those. So we would subtract the difference for each monkey, and this would be paired data. But we're trying to estimate, so it's definitely a confidence interval, but this is not two different means, but the mean of the difference, not the difference of two means. Are people happier after getting married? 100 people are asked on a scale from 1 to 10 how happy they are 1 year before marriage and then 1 year after marriage. All right, so this is definitely a matched pair. Again, you're asking the people before they're married and then a year after they're married. So each, not two independent samples, it's the same set of people doing two different things. So this is matched pair. It's a hypothesis test because we're not asking how much happier, we're asking are they happier? So it's a yes, no. Is the difference between their happiness is the same before and after, or is it, is it greater? Is their happiness greater after marriage? All right, so your homework for this last part of 10.2 is 6 problems, 4 of which require your 4 steps. So use the example we did in this video as a model. Again, we encourage you to use your calculator, save some time, right? Use your calculator. We really just want you to interpret the results more than have to do all the calculations by hand and use a t-table and all that. So just make sure that you're following your 15 components that we saw in the example that we saw in the video. And of course, this homework is due next class.